Let's say you've been working on a new project for quite some time and you're now ready to create the finalized circuits more permanently on a perf board. The only question remaining is how to power it. Now personally, I would always recommend adding some kind of USB ports, because this way you can easily power your circuit through common power banks with 5 volts. The reasons for that are that nowadays pretty much everyone owns a power bank. They are portable and, most importantly, they offer a few very important electrical protection features. They not only shut off the power bank if a short circuit occurs while you're making stupid mistakes, but they also do not allow you to apply a reverse voltage to your circuits, which could lead to a lot of damage. And with the power question being answered, your DIY walkie-talkie project seems to work just fine. But anyway, now let's imagine you're creating a new awesome project that you want people to power with their own power source, like all kinds of batteries, solar panels and whatnot. In this case, you will always need some kind of protection circuit that prevents an undervoltage, overvoltage, reverse voltage, and let's also throw in overcurrent, because people will always find a way to fry your electronics. I faced a similar problem while designing my LiPo Supercharger circuit, which I presented you in a previous video. It can output 5 volts and 12 volts, which is super handy to power all kinds of portable electronics. But once again, there's always a possibility that people will create an overcurrent or short circuit on the outputs, and I do not want my circuits or battery to blow up. That is why I use such an eFuse IC, which can pretty much solve all of our protection problems. And in this video I will show you how it is being used in my LiPo Supercharger circuits and how we can use it for a wide variety of electronics projects. Let's get started! This video is sponsored by JLC PCB. Feel free to visit their website jlcpcb.com to not only find out what awesome PCB and assembly services they offer, but also to easily upload your Gerber files and thus order affordable and high quality PCBs quickly. First off, where can we find such eFuse ICs? Because the selection on eBay is honestly not great. Well, simply go to Mouser, search for eFuse and then select the Hot Swap Voltage Controllers category. Feel free to sort by price. And there you go. But before actually deciding on one of those ICs, we have to make up our mind about the protection features we need. So, as an example project, I will go with a simple Arduino Nano that blinks an LED every half second, because this way we can visually see if the circuit works or not. For protection, I want an overvoltage limit above 6 volts and an undervoltage limit below 4 volts, because between 4 volts and 6 volts lies the reliable working area of the circuit. I also want to limit the current to 200 milliamps, because that is more than enough for the project, and 200 milliamps will not kill the circuit over time in a reverse voltage situation. And for now, I will not include a proper reverse voltage protection, but we will talk about that problem later. Okay, now with the voltage range and current limit in mind, I started browsing through the available ICs, and immediately found this TPS 259621 IC. Not only is it relatively cheap with a price of 86 cents, but it also comes in a package, aka form factor, that you can easily solder by hand to breakout boards. It also works with voltages between 2.7 and 19 volts, comes with an adjustable current limit from 0.125 amps up to 2 amps, and also features overvoltage and undervoltage protection. Perfect! And due to those properties, I also used the exact same IC in my LiPo Supercharger circuit. So after receiving the IC and soldering it to a breakout board, I added mail headers to it in order to place the IC next to my Arduino project on the breadboard. But how do we connect the eFuse to the project? And how do we have to select the additional passive components in order to properly set the protection features? Now of course, you could simply browse through the 47 pages of the well-written IC's datasheet in order to find that out. But what fun would that be? Instead, let's rather have a closer look at the circuitry around the eFuse IC in my LiPo Supercharger circuit, in order to determine what each component does. First off, it is pretty self-explanatory that the ground pin connects to ground, or that the in pin connects to the input voltage and the out pin connects to the project. So let's just do this simple stuff on the breadboard. Next we can see how the enable undervoltage pin is put up to the input voltage through 100 kilo-ohm resistor. That means that according to the functional block diagram of the IC, this non-inverting input of the comparator is connected to Vin, aka 3.7 volts in my case, which always turns it on and thus enables the current flow from the input to the output by activating the internal MOSFET switch. But of course, we can also use this pin for undervoltage protection. By utilizing this formula, I came up with this resistor network, which built up on the breadboard creates a voltage for the undervoltage pin that goes just above 1.2 volts at an input voltage of around 4.5 volts. That means that as soon as the circuit was finalized on the breadboard, the project will only get powered at a startup voltage of above 4.5 volts, and it cuts the power to the project at a voltage of 4 volts. Perfect! Next we can have a look at the overvoltage pin, which is not connected to anything in my LiPo charger circuit. According to the datasheet, that means that the output voltage is clamped to a voltage of 13.58 volts if an overvoltage threshold value of 13.77 volts is exceeded. Luckily, there's also an option for clamping the output voltage at a threshold level of 5.7 volts, which results in an output voltage of 5.45 volts, by simply connecting the pin to ground through a 400 kilo-ohm resistor. So I did just that with a 470 kilo-ohm resistor, and as you can see, if we exceed the voltage limits, the output voltage gets successfully clamped to 5.35 volts. But keep in mind that the excess power that the eFuse now has to get rid of in the form of heat does obviously heat it up. Do not worry though, because the current flow is stopped automatically at a certain temperature, because the IC also comes with an over temperature protection. Okay, moving on. The last important pin is the ILM or current limiting pin, to which normally one resistor is connected in my LiPo charger schematic. Now the IC pumps a constant current through this resistor proportional to the flowing current, and thus the resistor creates a voltage drop, which can be once again used for a comparator in order to trigger an overcurrent protection. This might sound familiar to you because I built a DIY overcurrent protection circuit before, which uses a similar functional principle, so feel free to watch that video if you want to learn more about that. But anyway, not only can we monitor the flowing current through the externally attached resistor, which is pretty handy, but we can also easily alter the resistance value according to this formula in order to set a current limit of 200 mA. And after adding this resistor to my breadboard circuit, you can see how the output current is limited to a value of roughly 200 mA. Now the IC also comes with a fault pin that obviously indicates when a fault occurs, and a DV/DT pin to which we can hook up a capacitor in order to decrease the inrush current. But those pins are just a bonus for me. because I'm already quite happy with all the protection results the IC achieved so far, considering that it was rather cheap to buy and only required a handful of passive components, which is why I would recommend such an eFuse IC to everyone. The only protection missing was a reverse voltage protection, which this IC does not offer. But according to one of my previous videos, you can easily build one by yourself. I did just that with the help of a P-channel MOSFET, and as you can see, it works perfectly fine. But of course, you can also invest a bit more money into a more advanced eFuse IC, which comes with reverse voltage protection and some other nice to have features. Then however, you will be forced to work with a not easy to hand solder package, so the decision is up to you. But anyway, I hope you enjoyed this video and learned a thing or two along the way. If so, don't forget to like, share, subscribe and hit the notification bell. Stay creative and I will see you next time!